Hello everyone and welcome to this presentation. My name is Thibaut WISSOCQ. I am a research engineer at the IEA Research Institute and I will present my work about the generation of simulation faulty datasets to IEA network fault detection using machine learning. This study is conducted with Nicolas Lamaison and Mathieu Vallée at the CEA and with the Fraunhofer Institute as part of the IEA DHC project. First of all, District 18 networks, as all technical systems, is subject to dysfunctions during their lifespan. Their faults often go unnoticed, especially in the network and in the substation, as pointed out by Werner et al. In order to boost their efficiency, it's important to develop robust fault detection and diagnosis methods. Artificial intelligence and machine learning algorithms can provide significant benefits in the detection, but only if data is available in sufficient diversity and quality. There, in the IEA DHC project, which is funded by IEA DHC, we aim at providing to the community a reference dataset to study fault detection and diagnosis in DH systems. We will consider simulation-generated data from Modelica models as a clean baseline for training machine learning models. Performance of machine learning models will also be assessed, as well as transferred to real-world systems in 2 steps. Therefore, in the presentation, I will present you the data generation methodology, then I will present some details on the model and the data generated for one example. Then I will provide you some early results on machine learning models and fault detection. The goal of the methodology for fault database generation is to select suitable models for fault simulation, and we assume here that each DHC component, as boilers or storage, is considered independently. It means that the faults will be simulated on each component. The methodology is composed of 5 steps. First, we identify and release the model in existing libraries, which are Modelica libraries. Then we identify each model features. Then we characterize the fault modeling capability of the model. We identify the suitable models for the most relevant faults. And we identify the development needs in the model if it's necessary. So here, on this table, you can find all the existing libraries that you use to identify and to list each DHC component models. I will describe you the methodology on one example, which is the boiler model. The first step is the listing of existing models for the boiler. So we found 13 models in 9 Modelica libraries. As you can see an extract here on this table. Then we characterize each model by its features, for example, how the efficiency is computed, the pressure drop model, or if its losses are considered or not. Then, for each identified and potential fault, for example, the effect of ambient temperature or the loss of efficiency that are listed here, we characterize for each model the fault modeling capability. Based on these elements, we identify the suitable model, and for our case, we choose the boiler no control model from the XLib library. We applied the same process on each DHC component, the boiler as we saw before, the head pump and chiller, the solar thermal plant, the network which is composed of pipes, valves and pumps, the substation and the hot water storage model. And for each model, we identify 2 or 3 faults to be simulated and a short list of models. The models come from XLib for the boiler and the heat pump, and from IPSA for the hot water storage. For the solar thermal plant, the network and the substation, the models come from our private library for practicity reasons. But these models will be released as open source models in the future. This is an overview on the boiler component and the fault simulation framework. We find here the boiler from the XLib library, the boiler no control model, which is modified to simulate dynamic faults on efficiency, which is based on part load and inlet temperature, and to simulate faults on heat losses. We added also a random noise on the low heating value of the gas in order to introduce some variability in the result. And the component is subject to boundary conditions that are the inlet mass flow rate and an inlet temperature, and also a supply temperature. And the boiler is regulated by the supply temperature with a controller. The boiler may be subject to some faults on the thermal conductance and some faults on the nominal efficiency. And the faults are simulated thanks to a Python-based fault generator. We define the profile type of the fault, which is either a step or a ramp. We define its start time, so when the fault appears, and its intensity, which depends on the model and the fault type. The intensity is between 0 and 1. 0 means that there is no fault, and 1 is the maximal intensity available. Here we use random parameters to generate the faults in order to avoid too much regularity when using machine learning algorithms. And for each boundary condition, so here we have 13 time series, we have one reference simulation without a fault, and we have 3 times 100 simulation with fault on efficiency, heat losses, and both, and we have almost 4,000 simulation with a 5 minutes sampling. Here you can see some results on the boiler component for 2 different simulations. And this figure compares a boiler without any fault in blue and the same boiler where 2 faults appears successively. First, an increase of heat losses on this graph, then an abrupt loss of efficiency, about 10% on this graph. And the top-bottom graph shows the impact on the fuel power and on the fuel consumption. We can see that only the strong loss of efficiency is noticeable when observing the impact on the fuel power, and we can see also the impact of the random noise of the low heating heat value of fuel on the gas consumption. We expect that machine learning algorithms to be able to detect and distinguish those faults, especially the fault on heat losses. Finally, here we present some very early results about the application of machine learning algorithm for the detection of fault. We have tested different machine learning algorithms, mainly on the boiler efficiency for now. If you focus on the boiler, the results are good for the detection of fault on efficiency. The best algorithm is KNN, K nearest neighbors, with an accuracy of 0.99. You can see more detailed results on the right of the slide for 4 different faults on the efficiency, 1 ramp and 3 steps. The blue curve corresponds to the actual value of boiler efficiency, and the gray curve corresponds to the boiler run, 1 if there is a fault and 0 if not. In green is the correct detection detected by the algorithm, and in red is the incorrect detection. As you can see, most of the points are correctly detected because they are in green, and the red points are concentrated at the beginning of the fault, especially when it is a ramp. We expected that result because the fault is still minor at this moment. And we also can see 1 point due to the impact of the noise of the low heating value of the gas. And we are still working on the other faults and the other components, but we have already seen that the detection of heat losses and efficiency at the same time are not as good as the detection of the efficiency alone. To conclude, we develop here a reconductible approach for fault database generation of DHC component, and the simulations rely on open source model from Modelica libraries. We provide a reference dataset for fault database of several dozen of millions of instances, and we applied machine learning algorithm for boiler efficiency fault detection. In the future, we will publish the Python scripts for fault simulation and the dataset in a public repository like Kaggle or GitHub. And we want to improve the detection of faults with machine learning and extend the results to the other DHC components we have in a network. Thank you for your attention.